make sure you can do each of those forms for the eye drop, or for the isotonicity. So let me go ahead and try to work through the first ones then. So starting with the zinc sulfate, 0.25%, that's our drug at the concentration we need. And the boric acid says QS. It doesn't tell us how much boric acid to use. Why are we even using boric acid? Our tonicity adjuster. So the amount of the boric acid is simply the amount we need to make the final product isotonic. And we're making 15 milliliters. So where do we start? We start with our drug and find out how much it affects the isotonicity. So let's take its delta TF 1%, which means for every 1% concentration of zinc sulfate, I get a 0.09 degree depression in temperature. So that was given. Then I'm going to take the desired concentration. I don't want a 1%, I want a 0.25% concentration. So if I set that proportion up and cross multiply, I get x times 1 equal to 0.09 times 0.25, and so I get my answer there at 0.0225 degrees. That's how much my concentration of zinc sulfite will lower the temperature. Here's the trick for the test, and I'm making sure, what's my target? Where do I need to go? This won't be provided to you. What do you have to memorize? What is an isotonic freezing point depression? 0.52, that's my target. So from my target, I subtract what I'm getting from my zinc sulfate. So the difference between that is 0.4975. So that's the amount of freezing point depression I still need to get. What am I using to provide that? Boric acid. So let's take the information I have for boric acid, bring it down here and say 0.29 degrees Celsius for every 1% concentration, equal to what I now know is how much freezing point I need. I need a 0.4975 degree depression over X. And now I'm solving for, and make sure you see that, you're solving for a value as a percent concentration. So when I do the math, 0.29x equals 0.4975, divide both sides by 0.29, I get 1.75, and it's a percent. It's 1.72, if I said that wrong, 1.72% concentration of boric acid. All right? That's my answer, but it's not my answer. It's what I need, but I still need to figure out some more stuff. So if this is a concentration I need and this is the volume I'm making, then let's take the 15 milliliters times my concentration of boric acid at 1.72 grams per 100 milliliters. Milliliters cancels, and that's the actual weight of boric acid I need to make my product isotonic. And if we had just solid boric acid, we would be done, but that would be too easy for Larry. I gave you a 10% solution of boric acid, not a powder. So let's take my target for boric acid, which was what we just solved for, 0.258 grams. Take my concentration that he gave me at 10%, which means 10 grams per 100 mils, but I need to make sure I put 100 mils on top so that grams cancel. So 0.258 times 100 divided by 10 gives me 2.58 milliliters. That is the volume of my 10% benzalkonium chloride solution, or boric acid, I should say, boric acid solution that provides the boric acid I need to make it isotonic. So the question wanted the water. So again, water will be the total 15 milliliters from the prescription minus what we're going to be using from the boric acid solution, and the difference, in this case 12.42 or 12.43, depending on how you round it, would be the correct answer for the volume of the water. So 12.42 milliliters of water added to 2.58 milliliters of benzalkonium chloride solution plus the weight of the zinc sulfate would make our final product. Everyone okay with that? All right, so the approach with the sodium chloride, I won't say is harder, but it's different, and you start in different places. So in this case, I know exactly how much drug I need, okay? What am I using to adjust the tonicity is benzalkonium chloride, so whatever amount of that I need. But here's the trick on this. It is, again, instead of a 10% solution, I made it even harder. I called the strength a 1 to 15 concentration solution. All right, but we've done ratio strength, so that's not hard for you. We'll just do 1 gram per 15 milliliters. That's a weight per volume concentration. So we'll use that later. Where does it start? Because it starts with what I know. I know how much antipyrine I need therapeutically. So if I'm going to make 20 milliliters of this eye drop, and it's going to have a 2.95% concentration weight per volume, I multiply by that, then I can get the weight of my antipyrine. That's how much I need. but I have no clue what its tonicity effects would be. Let's convert it to how much equivalent sodium chloride that mimics. So if I take that amount of antipyrine and use its E value, and this is again the trick here, E value of 0.17 means what? 0.17 grams of sodium chloride. The number goes with the grams of sodium chloride per gram of drug. And in this case, since we want to convert from drug to sodium chloride, we multiply so that grams of drug cancel, and I end up with equivalent grams of sodium chloride. So when I multiply that, I get 0.1 grams of sodium chloride. That's how much my 0.59 grams of antipyrine mimics. That's what it's like in solution. That doesn't tell me where I need to end up at. That tells me what I have. So the next question to ask is, how much sodium chloride do I need? What's my target? So I'm making 20 milliliters. That comes from the volume I'm making. Here is the other thing you have to memorize for the test. What is an isotonic sodium chloride solution? It's one that has 0.9% weight per volume. Since I've memorized that, that's the amount of sodium chloride I need, 0.9 grams per 100 mils, times my 20 mils would tell me how much sodium chloride I need for just 20 mils. And for 20 mils, I need 0.18 grams. That's my target. That's what I need to have. So let's start there and subtract what I'm getting from my drug. I'm getting 0.1 grams from my drug. So 0.18 grams minus 0.1 grams means I need 0.08 grams still. That's what I would need to add to make it isotonic. But I don't have sodium chloride, I have benzalkonium chloride. All right, so I need to convert from the weight of the sodium chloride that I still need and convert it to the weight of benzalkonium chloride that would be equivalent to that sodium chloride. And in this case, do you see why I'm dividing by the E value here? Because it's 0.16 grams of sodium chloride per gram of benzalkonium chloride, so I need sodium chloride in the denominator, so I'm going to take 0.08 grams divided by 0.16 grams to convert it to grams of benzalkonium chloride. Are we done? God, we still got to go because that's the weight. Unfortunately, once again, we don't have solid benzalkonium chloride. We have it as a liquid. So if this is the weight of the benzalkonium chloride I need, then I have to take my concentration, and this is where I have to re-express my ratio strength as 1 gram per 15 mils, put grams in the denominator, so I'm going to multiply by 15 so that I get a volume. And doing that gives me 7.5, and that's 7.5 milliliters of that 1 to 15 concentration solution, because that 7.5 mils gives me the weight of benzalkonium chloride I need. So if that's the volume of the solution I need, then clearly I take the total I'm making, 20 milliliters, minus the amount of that volume of that solution, 7.5 mils, means that I would have 12.5 milliliters of water. All right. Questions on that? Trying to slowly walk through that. These are endless practice problems, so I can't emphasize it enough. There will be, I'm just be honest with you, each one of those are on the exam, so make sure you can do those. All right, I'll go through these a little bit more quickly because there's a little bit of repetition for questions kind of in the middle here. This is about milli equivalent, so going from millimoles to milligrams to millimoles to milliosmoles. In this one, there was a trick though. For question 3, part 1, when it's asking for how many milliequivalents of potassium does the patient consume each day? Well, it would be 1 tablet's worth if they only took 1 tablet a day, but what are they taking? They take 1 tablet 3 times daily. Did you notice that in the question there? That makes it a little bit of a trick. So that's 1 tablet, but they're taking it 3 times a day. So these are the amount per tablet. So when I set this up for solving for potassium, the first thing you'll notice, I say, okay, I'm taking 1 tablet per dose, but I'm taking 3 doses per day. So I'm going to take 3 times. And so now I'm interested in potassium. There's only one ingredient that has potassium, and that's the 155 milligrams of the monobasic potassium phosphate. So I'm bringing the 155 milligrams down, so 3 times that, since I'm taking 3 tablets per day. Then that's how many milligrams I would have. To convert milligrams to millimoles, I have to take the molecular weight. So there's the molecular weight, and that would convert, if I go through that far, I would get the 3.4 millimoles of the monobasic. All right, so restarting with that, though, I want to get to milliequivalents. I have to look essentially that there is 1 potassium for every 1 monobasic potassium phosphate, so it's 1-to-1 there. Then to convert from millimoles of potassium to milliequivalents, I look at the valence. It's a plus 1, so it's a 1. So 1 to 1 gives me 3.42 milliequivalents of potassium. Everyone seem okay with that? Step by step. The biggest trick for this part was just the fact that there were 3 tablets in there, okay? All right, now how many milliequivalents of sodium does each patient get? Well, that's a little more complicated because there's sodium in the dibasic sodium and there's sodium in the monobasic sodium. So we have to do it twice. So I'll show you my work for both of them. If I just do, well, let's focus on one at a time. So again, they're getting 3 doses per day. For the dibasic, if I come down here, that's how many milligrams per tablet. So 3 times that. Its molecular weight is here. So if we divide by that, we convert it to millimoles. Here is the trick. What is the formula for dibasic sodium phosphate? Is Na2HPO4. So do you see where this 2 comes from? It's because you get 2 sodiums from every parent molecule. So for every 1 millimole of the dibasic sodium phosphate, there are 2 sodiums contained in there. So you have to multiply by 2 just to get to the millimoles of sodium. To get to milliequivalents, again, the valence on sodium is just 1, so it's just 1 across there. Do that math, and I got 36. All right? So that's very different. If I just show you for the monobasic sodium, everything is the same going through here, but when we get to this step, looking at the formula, it's just 1 to 1 because there's just 1 sodium in the monobasic. So that's why in the end there, we only get 3.25 milliequivalents. Doing the math across, just adding them all up gives me the total for sodium for the day. Okay? Hopefully that's okay. Don't go from milligrams to millimoles to milliequivalents. But make sure you look at the formula and the valence. All right? Now, in this case, I do want just millimoles because we dose phosphorus in millimoles, so I'm not worried about the milliequivalents there. We are getting phosphate from all 3 of those. For the sake of time, I won't belabor all of those, but in the nice thing here is you'll notice there is just 1 phosphate in each of those molecules here, so it's 1 to 1. So all the difference is the different molecular weights and different starting amounts for each of those, but otherwise the process is exactly the same. So I won't belabor that point. You can check my numbers on the key. All right? This is a little more interesting, all right? So this is about milliosmoles and milliequivalents. I should start with milliequivalents. So in this case, an additional 15 milliliters of a 20% potassium chloride solution is added to a 250 bag that already contains 5% dextrose and 0.45% sodium chloride. So the first question is about the potassium, and I want it in milliequivalents per what? Per liter. That'll be a little bit of a trick here. So let's start with just determining milliequivalents. Well, it'll be based off of how much we put in there. We're putting 15 milliliters of a 20% solution. Okay, and even though I don't show my answer there, are you okay with that? We added 15 milliliters of a 20% solution. So 15 milliliters times 20 grams per 100 milliliters gives me the weight of potassium in grams. So to convert that to milligrams, I'm going to multiply by 1,000. That puts me in milligrams. How do I convert milligrams to millimoles? Is I divide by the molecular weight. So when I divide by 74.5, I now know the number of molecules of potassium chloride. There's 1 potassium and 1 potassium chloride, and the valence is 1. So there's 40 milliequivalents of potassium. But I wanted it in what? Milliequivalents per liter. So I need to figure out the volume. I start with a 250 ml bag. I'm adding 15 milliliters to it. So I get 265 milliliters. Convert that to liters by dividing by 1,000. I would argue this potassium is in 0.256 liters. So if I just set that ratio up, I have 151 milliequivalents per liter. Okay. Does that make the question a little more difficult? Yes, no, you should be able to know 15 mils of a 20% solution. That's my starting point for the potassium. And then you go through and convert it to milliequivalents and then account for the volumes, all right? Now, this is what's new, and there's a lot of work with this because what is going to be osmotically active? The potassium chloride are going to be particles. The dextrose is particles. The sodium chloride is particles. So we're going to have to count all of those particles to be able to determine the osmolarity, which again is millismoles per liter. So we'll need to do that. So Okay, I'm just going back from the beginning here, and we've kind of, well, we've quickly gone through 15 milliliters of a 20% solution, converted to milligrams, still divided by the molecular weight, converts it to millimoles of potassium chloride. So this first line is exactly what we did on the previous page up to a certain point. But now that I have millimoles of potassium chloride, I don't need to go to milliequivalents. I need to figure out how many particles. So what happens when potassium chloride dissociates? How many particles do I get? I get 1 potassium and 1 chloride. How many is that total? 2. So I'm going to multiply by 2. I get 2 particles in the sense of milliosmoles, 2 of those for every 1 molecule of potassium chloride. So that's where I got the 81 from. Okay? Now, starting from the sodium chloride, if we start with the sodium chloride, we're doing 250 mils of a 0.45% concentration. That converts it to grams. We convert grams to milligrams. We take the molecular weight here, divide by that so that we convert from the weight of sodium chloride to the number of molecules. And from millimoles, what happens when sodium chloride dissociates? 1 sodium, 1 chloride. So that's where the 2 comes in again. That gives me the milliosmoles from that. All right. Similarly, for the dextrose, 250 mils times 5%. Okay, that converts it to grams of dextrose. Convert grams to milligrams of dextrose. Use its molecular weight to divide by it to get to the number of molecules. All right. Dextrose is a non-electrolyte. It does not dissociate into anything. It stays the way it is. So for every 1 molecule of dextrose, you get 1 particle. It's 1 to 1. So in that case then, we get 63 milliosmoles. So we add all of those up. So if we add all of those 3 up on total and divide by what we talked about before is 0.265 liters, that's the total volume in liters, I got 691 milliosmoles per liter. Okay? Oops. Any questions with that? That's a lot of work because there was quite a few ingredients in there. I don't know that I'd give you quite that many ingredients on the exam, but certainly 1 additive to 1 bag would not be an unreasonable thing to be able to calculate. So I like this question. This is a good example. The kinds of calculations you have to do to count particles, not milliequivalents, but particles in milliosmoles. All right. So now we've got an electrolyte solution that I gave you on the question, all the different amounts. And so the first thing, and the reason I chose this question, to be honest with you, is it starts, if you look at the label of these electrolyte solutions, it started with milliequivalents of everything. So you had to go from milliequivalents and go backwards because the question wants milligrams. So I won't belabor the point here. This is the exact thing we practiced, but going backwards. So if I just do for the sodium, if I tell you there's 17.6 milliequivalents of sodium, all right, let's go from milliequivalents to millimoles because the valence is 1, so there's 1 MEQ for 1 millimole. And again, there's 1 sodium in sodium chloride, so it's 1 to 1. That gives me 17.6 millimoles. Then I use the molecular weight and I multiply by the molecular weight to get to milligrams. Do you see where it's the same thing going the other direction here? So the biggest trick might be the potassium citrate because again, the potassium that I know is 21 milliequivalents and there's 1 MEQ per 1 millimole since the valence is 1. But here's the truth. Look at the formula. There are 3 potassiums for every 1 potassium citrate. So I have to divide by 3 to cancel my millimoles of potassium to end up in millimoles of potassium citrate. Then I just simply multiply that by the molecular weight to get the weight. But do you see where this 3 would be what's tricky on the test? So everyone see why you divided by 3 there? Because there are 3 potassiums in 1 potassium citrate. Okay? So I won't belabor the point too much. I'm kind of running out of time here. So now we go to the osmolarity. And I would tell you here, the reason I stopped here is here in this steps, we have calculated the millimoles already of each of my 3 ingredients. And now instead of going over here to weight, let's go from here to particles. So if I start with those same numbers, okay, these are the ones that were already on there that we've already done. So those are the values we already had. Let's count particles. So for sodium chloride, there's 2, 1 sodium, 1 chloride. This is a little bit of a trick here. What is the number of particles in potassium citrate? 4, 3 potassiums and 1 citrate. So that's why we multiply by 4. And again, with zinc, there is 1 zinc, and there we have it. The rest of it is gluconate. So, oh, no, there are 2 gluconates. Did you catch that? 1 zinc for 2 gluconates. So 1 zinc, 2 gluconates gives us 3 total for the number of particles generated from that number of millimoles of zinc gluconate. All right? Lastly, there was some dextrose in there as well. I won't belabor that point since it's 1-to-1, since it's a non-electrolyte. So once we determine all of the milliosmoles, we add them all up. This was for a 1,000 ml bottle, so that's equivalent to 1 liter. So we divide that out and got 190 milliosmoles per liter. All right. So again, I'm running out quick here. This is a good example of the kind of question, it's not the only question I'll ask, but from chapter 14 when we did that big TPN calculation. So this one is just jumping way ahead to the end when we're calculating the electrolytes. And again, I give you a feed weight here. And for sodium, it is a weight-based amount per day with this concentration of an additive. So make sure you understand, to figure out the volume I would need for this patient, if their feed weight is 84 kilograms, and they have 1.5 milliequivalents per kilogram. I just multiply by that. But to convert from milliequivalents to volume, I need to divide by the concentration. So it's 4 milliequivalents per mil. I get 31.5. That's easy. Let's do the phosphate real quick, because again, I told you just to get 24 millimoles of phosphate. Concentration is 3 millimoles per mil. Divide 24 by 3, I get 8 milliliters. Bear with me, there's a point to this. All right, how much potassium chloride do I need? Oh, there's a little bit of a trick here. So let's start with the potassium. I need 1.5 milliequivalents per kilogram per day. The feed weight is 84, so I need a total of 126. But I just solved for 8 milliliters of potassium phosphate to provide the phosphate. But it has a concentration of 4.4 milliequivalents per mil of potassium. So 8 times that tells me how much potassium I will already be providing. So I take my total minus that, and the difference here is the amount that I need from the sodium chloride. So this is the concentration, or the amount I should say, of the potassium chloride that I'm going to use here at 2 milliequivalents per mil. Divide that by 2, and that gives me the volume of the potassium chloride. So do you see the relationship between potassium chloride and the volume of the potassium phosphate? These two volumes have to total that amount of potassium. So it's the two together that add the total amount of potassium, okay? And I'll spare you the calcium and the magnesium. Those are all pretty straightforward. Then you all add them up at the end there. So